Okay. I was going to go over some of the stuff I forgot to do in the first one. And we didn't talk very much about transformers on how they actually work. We mentioned mutual inductance. I don't think I explained it. And it's where, because they're on a common core, whether it's air or some ferrite material or iron or whatever, they share the same magnetic field, so that if you put a current through one of the windings, that magnetic field that's created causes a current or voltage in one of the other windings, and you can have more than two. And that's what's called mutual inductance. And from the impedance standpoint, you see the effect of both of them. Okay. Depending on how many turns are on each side will determine what the inductance actually looks like. So as that field increases, it increases the voltage or current on the other winding that isn't directly powered. And I had my Lenz's law demonstration, which Aaron and Samantha won't be able to see, but I'll let Byron do it. We have a supermagnet and a piece of PVC pipe, and he's going to time how long it takes.
Yep.
That was quick. I'd say it's less than a second.
Okay.
Now we have a piece of 3/4 inch copper pipe, and he let it go, and he let it go, and it finally came out. So the question is, why did it take so long?
Yeah.
So what is that?
Only
10
5 seconds.
5
Yeah,
seconds.
yeah. I don't know.
It's because the copper
I think
pipe
that quick.
is acting like a one-turn coil that's shorted together. So as that magnetic field moves through that coil, it is creating a current that's creating an opposing magnetic field that's trying to prevent the magnet from falling, which is what happens in a transformer, basically. And if there was no losses, the magnet would be stationary. But because there's some loss in this real world, it allows one field stronger than the other. It allows the magnet to fall.
Who was the guy that dropped the apple?
Newton.
He hasn't gone nuts on this stuff.
That was Lenz, Lenz. A lot of the magnetic stuff.
So I suppose you can measure it.
I tried,
Ooh.
and actually, I could only see it. I wrapped some wire around it, and I could only see it when it passed through the external coil.
What's that?
Huh?
As you dropped it through there, it created some polarity.
Yeah.
Yeah, so let's drop it through a few more times. See what it does.
Are you using the same top and bottom?
Yeah.
Yeah.
It's slowing down.
Just so you guys know, they're playing with the magnet.
It is, it's slowing down.
This was an MIT demonstration. You can find it on YouTube. Okay, we talked a little about turns ratio on the transformers. And that's how it determines whether it's a 1-to-1 or a step up or step down, depending on the ratio of the turns. But it also affects the impedance. And the impedance of the transformer is going to be the square of the turns ratio. So where that becomes important is if you're trying to do a matching transformer for an antenna, you need to know what the impedance transformation ratio is So it's the square of the turns. So if you wanted a 49-to-1 transformer, which you'd use on an end-fed half wave, you'd have a 7-to-1 turns ratio. And probably have something like 3 turns on the primary and 4 turns or 24 turns on the secondary, right?
For
Something like that.
yeah, for your 60-40-1. A lot of times they'll tell you that the crossover, if you're doing your crossover turn, that count that as a full turn. But if you measure it, it's actually less than a half turn. So that's something to think about too.
Okay. I always get confused on the turns and I always have to go back and count them several times
Yeah, anytime.
and then add one or take one off because okay. Okay. We didn't talk a lot about AC waveforms, and there's a lot of other than sinusoidals. One of them is square waves, and we mentioned earlier about distortion in amplifiers, where you get flat topping or clipping, where it's starting to look like a square wave, and what effect that is. So this thing showing the basic 4 waveforms.
How you burn up your driver, your audio driver.
But also how you can recreate a square wave by adding up all of the odd harmonics in this series, where you take the third harmonic with an amplitude of 1/3 and the fifth as 1/5 and so on and so forth. And even, I mean, only doing that many, you can see how it's a square wave with ripple on the top. So the more additional harmonics that you put in there, that would eventually make that into a perfect square wave if you had an infinite number of harmonics. So when you have an amplifier and you're getting clipping, where your sine wave is starting to get this flat top, it means it's generating all these harmonics, which is why it's a bad thing.
Then your tweeter smells like the smoke right now.
Okay. The other thing we didn't talk about was RMS. I think we might have mentioned it, but it's really a way of measuring the equivalent voltage or current of an AC waveform to a DC waveform. So the RMS value of a sinusoidal AC wave is the same value of heat generated by the equivalent DC voltage. So it's essentially the area under the curve. And the way you get there is taking the peak value of the AC wave, which is from 0 to its highest point, and multiplying that by the square root of 2. And that gives you the root mean square, or our close approximation to it. It turns out it can get complicated if there's any DC component to it where there's an offset. It turns out to be the square root of the AC RMS plus the square of the DC part to get that result. I'd never dealt with that, but it does make sense. If you had just the peak to peak value, like if you looked at one of these plots or you looked at it on an oscilloscope, you need to take half of that to get the peak value and then multiply it by
that would be the mean.
by 1 over the square root of 2. Be 0.707 times the
Peak.
peak value. Here's an example of a nice sine wave. And we have our peak voltage and our peak to peak voltage. So this is actually equivalent to your AC power. So it's actually going to be around 270 volts peak to peak. Even though you think it's 120, it's 120 volts RMS. So 0.707 times the peak value is going to wind up giving you that 120 volts, which says it would generate the same amount of heat or do the same amount of work as 120 volt DC.
So that makes RMS very useful.
Yeah, that's why you use it. And it works great on a sine wave. If you got others like a triangle wave, I think you have to use the square root of 3 or something, and it gets a lot more complicated. Fortunately, we tend to deal with sine waves. It's only those other waves when you're not doing something right. And here was the thing we never talked about, the house wiring, showing the normal setup where you have a distribution transformer out on a pole or maybe underground. If you're fortunate enough. I still have a power pole and a power line, which is too close to my antenna, but that's life.
The buried owns about 2 years ago.
The feed coming into your house is going to be a 240 volt RMS signal that's center tapped, okay, with the and that's the neutral. As soon as that comes into your service panel, okay, it goes to a ground rod outside the house. You also have what's called the safety ground that's connected to that neutral at that point only. And that's will show up as your green wire in your house wiring. Whether it's 240 or 120, you're going to have a green wire. If it's a normal 120, which is most of what you're going to have, you're going to have a neutral or white wire and a black wire, which is the hot wire, and the safety ground. The purpose of the safety ground is it will be connected to any metal enclosure that is plugged in, so that if there's a short circuit from the hot side, okay, it gets shorted to the safety ground out to the ground outside instead of going through you. Nowadays, most things like your drills and all that kind of stuff are double insulated in plastic, but most of them still have a 3-wire cord, so they do have a safety ground in them. In the case of 240, you only have 2 hot leads for normal distribution, plus the safety ground. Now, if it's 240 going to a stove or a range, it will also have a neutral. So they get 120 plus 240 out of those 3 wires. My shop is wired that way with the neutral. So I have all the receptacles split. So one side of the receptacle is the black phase, the other side is the red phase, and they share a common neutral. So that if you've got stuff plugged into both of them, it reduces the current flow through the neutral because they're in opposite directions. So if it's perfectly balanced, you'd have no current flowing in the neutral.
So you could flip your when your waveform's on 2 or 3.
Say what? Oh,
You could flip one of those
yeah.
to show it's out of phase.
Oh, yeah. But I didn't.
Yeah. I know it's going to keep you up that night, but
we can pretend.
Yeah,
Okay, so here's see, what did I plot?
that looks like your two phase.
Yeah, that's the your 120 volt in, which is going up to about 170 volts. This is 100 and 200. So the peak to peak is going to be that, what was it, 270? Close to 300 volts. The oh yeah, this is the other phase.
I think someone told me that around here we run now is 120 degree, three phase. And you
Yeah, but
get
this is not three phase. This is sort of, nobody calls it two phase, but with
Yeah.
the neutral, it's actually two phases that are 180 degrees apart. Whereas your three phase, you're 120 degrees. And if you were
Yeah.
four phase, you'd be 90 degrees. You don't
But,
see much of the other phases, but most
Usually-
power stuff, big motors, power transmission is three phase. Because you have less current
Commercial buildings.
that way. Go ahead.
I said you'll see that more in commercial buildings than residential.
Yeah. Most people only have a 240 volt going to their dryer or to their stove. Don't normally have a 240 volt outlet unless they have it specifically put in. Or you have a 1500 watt power amplifier for your radio. You probably need 240.
So if you're 180 degrees two phase, it would be 240. But if you have a three phase system and you're running two phases of it, then you want 208 volts.
Yes,
Yeah.
I believe it's 208.
So there's also a three phase with what they call a wild leg or a bastard leg or whatever, where it's got 240 coming in and then it's got a 208 coming in as well.
Yeah.
Ooh, nice.
Plus, you can have it in a Y or a delta, which affects it too. That was many, many years ago in electrical machinery lab. Okay, and we didn't talk about power measurement. And you normally use a watt meter. In amateur radio, you're mostly concerned about the power going out to your antenna. So we use a directional watt meter that actually measures power in both directions. It can measure forward power going to the antenna and reflected power coming back. In a lot of cases, like in the picture shown, it's a cross needle display, and there's actually two meters in there, one over here in each corner, and reflected power drives one of them, forward power drives the other, and where they cross on these red lines on the chart shows you what the SWR value is for that. It's a complicated ratio of the reflected and the forward power. The other thing that we measure is peak envelope power. Like I show in the diagram, when you have a modulated carrier wave, okay, the peak envelope is the highest point of that envelope, not the average. Now, when you have an unmodulated carrier, the peak envelope power is the same as the average because there's no modulation. So they will be the same. Use that same value. That's a test question about the difference in the two. And I think the way they do the question is they give you an unmodulated carrier wave and want to know what the peak envelope power is. It's the same. We also have effective radiated power where you take, if I got this right, the peak envelope power and multiply it by the gain of your antenna system.
So much truth.
Well, they assume because when you have a high gain antenna, you're concentrating the power. I mean, the same power, you don't actually gain anything. You just redirect it like a flashlight. Okay, forward, reflects the beam forward. Well, if you didn't have the reflector there, the same power is coming out of the light. Okay, it's just you're concentrating the beam. And that's the way beam antennas work. So they figure in the antenna gain to get the effective radiated power. So if you had a 10 dB gain antenna, you get an additional 10 dB gain in power as
Now,
far as ERP.
They haven't changed rules because it was the power that you're feeding to the antenna. At the antenna feed point is your 1500 watt limit, but your RF exposure is going to be your ERP.
Yes,
Okay.
yes, ERP, yeah, exposure, which apparently is something that's changing. I understand on the new general exam, there's more stuff going on with radiation exposure.
Which means I should probably file my,
Well, one of the things I guess they're going to insist on you actually keeping records of your calculated exposure. Before it seemed like it was something you should do. I think they're going to make it something you have to do. But it's easy. I mean, you just have to have it in your station log. And there's the ARRL site has a calculator, and you just put in the numbers, what your power is, what your duty cycle is based on the type of modulation.
Yeah.
Well, for different frequencies. From 30 to 300 is worst case. It's 1 milliwatt per square meter for humans, because your soft tissue like eyeballs and things are the most susceptible at those frequencies. And that's for a controlled environment. And then it's about half of that, I think, for an uncontrolled, which means your neighbor who doesn't know you're transmitting at them. So because they don't know it and stuff, you're not allowed to expose them to as much radiation. So you just plug in 4 or 5 numbers and it will tell you how far away you have to be within the permissible limit. And if you, for instance, do it on your walkie-talkie and do like 50%, well, I don't know if I did 50. If you definitely do it at 50% duty cycle, it says you need to hold that about 2 feet from your head. But I don't think, well, you're a lot lower power, but you could still go through the calculation. And since you got it right there, yeah. And they claim, some people used to work with a guy who put tinfoil on his head.
Oh, I thought those were aliens.
oh, now you could have, what's that? Colonel Jack Ripper from the Dr. Strangelove.
Oh, okay.
Only drink,
Yeah.
rainwater, distilled water.
You can also get these watt meters that have a digital display and will read out in forward and reverse and SWR in a digital display instead of trying to read the cross needles. Some people like those. I don't know. Mine's a digital one. Huh? Oh, yeah.
Keep your vital fluids.
Okay. Anything I forgot to talk about?
Well, let's see. Oh, we haven't talked about KC2 UFO.
All right, talk about KC2 UFO.
So KC2 UFO is a call sign that Dave Slauson uses for his club. Or
Sky watchers or something.
Sky watchers and communicators. So KC, keep calling to UFOs. Yeah. And he has a club structure that was unfamiliar to the FCC, and they were not going to allow it until he talked to them.
Yeah.
And they decided to allow it. He has a king and queen. Okay. And on the solstice, the king and queen switch, which is he and his wife. And that's how they, determine who's leading the club. But
The FCC forms want you to put the president and the vice president.
yeah. And they hadn't had a king and queen before.
Yeah.
So generally, Dave is noted for being one of the funner amateur operators around here, as far as special events. Like we had permission to use Ray's Cassis's station for the Mayan end of the world or 2012 or whatever that was. And Ray has, big Collins gear and all that stuff. So that was a nice station to use. We would do special events over at the Veterans, Museum for Memorial Day and Veterans Day.
I want to hear one.
Uh,
Volunteer.
well, it depends upon the politics at the time and who's leading, and how you get along in that environment. But I understand for the most part, it's good. So he would do those type events. He became no fun and was working too much, but that has changed. So he's getting back in, and now he's doing parts on the air type stuff. So I don't know whether he's going to start doing other special events.
Does he do your QRP stuff?
Sometimes. Usually he's doing parts on the air.
Okay.
So I think he came out last time.
When you were at Kelly Park?
Yeah.
I didn't see him when I was there, but I was only there for a
Okay.
little bit.
Yeah.
Here's Dave
Slauson.
Slauson.
K4UZM. But he's also a contrarian. So if you want a contrary opinion during a club discussion, bring Dave in. So,
Not that Viren isn't.
yeah. Like, we're talking about doing D-Star. I think to most digital modes, but especially D-Star and Fusion, because you have the AMB codex that essentially makes it proprietary.
Right.
Okay. And which makes it encryption. Okay. So the French telecommunication union decided, well, being it's encryption, it's illegal and it shouldn't be here. But that's only, governing body that's done that. And then it's basically, it's a social media app that you can have on your phone, but you need an FCC license to use it. So how is that amateur radio?
Yeah.
Well, it's no different than IRLP. You need a license.
Yeah.
How do you brought up a whole different world for me all of a sudden? How do they treat VPNs?
Yeah, that's a good question.
Who? The FCC?
The Papa Network in what are they calling the
There's an enterprise now that's new, that we just had to sign up to.
well they were taking some of the 5 gig privileges away from the amateurs.
Yeah.
And that was really screwing up a group called the Papa Network. but they had set up a lot of stuff in California for communication based on 5 gigahertz. And of course, with that much bandwidth, they could pass video for special events if they were monitoring walkathon, stuff like that. So that's caused a problem there. But here, it doesn't seem like that mesh network sort of is popular.
No.
Well, I don't see a whole lot of control factors on these VPNs either. Maybe I'm missing something.
Yeah. Everyone's relying on Spectrum or whoever to shoot their
Yeah. Everybody's getting one.
yeah.
Well, there's a lot of them out there, free and paid. I've been using Norton for years.
We just put in a whole new Dell server system and everything, and this enterprise VPN came up as a standard interface. I spent a couple hours on a Zoom call yesterday with Dell. That trigger always out.
Well, I run into a lot of things that aren't compatible with it, and I'll have to turn it off in order to get to certain sites or things.
Well, I think that mesh networks are going to be more and more as we go.
But I almost always have it on when I'm buying something on the internet.
Secure layers, man.
Right. And it does, cut down on tracking you because, you could look like you're on a server over in, Turkey or someplace if you want. I mean, you can pick your endpoint. I don't know how much that helps, but supposedly it does. I think Google tracks you regardless.
Oh,
I bet you do and don't know it. Because most people use Google servers to do their, yeah.
Totally control.
yeah. Steve has a good story. He had a HP laptop, I believe it was. But he got tired of the Windows update stuff. He had Windows 10.
Yep.
And so, he figured out all the virtual links and that stuff off. He was successful. Yeah. And then about a month or so later, HP calls him, Mr. Luchek, do you still have your computer? Are you still using it? A few weeks later, he was turned back on.
Okay. Aaron and Sam, you got anything before I stop recording?
No, I'm good on my end.
Nope, I'm good.
Okay. Did you learn anything?
I probably learned more than I was expecting, and I'm going to still have to do a lot of reading.
Yeah, me too.
Yeah, well, in order to pass the exams, you got to do practice tests. It doesn't matter, whether you take courses or read the books, you got to do practice tests.
Yep. Do about 2 or 3 times a week for 10 or 15 minutes and you should be good.
If you get up to 90% or better, you're good.
Yeah.
I'm working on that.
You don't need to get 100. You just need to pass, which is 74%.
Yeah,
And there's only 35 questions for technician in general. So.
Well, that's how I passed
questions
my
or whatever
FAA
it is.
exams. Haven't crashed a plane yet, so
Say that again.
I said that's how I passed my FAA exams and didn't crash a plane yet, so I should be okay.
Okay.
There you go.
All right. Well, appreciate coming. Let me know if you need anything else. I guess we'll start the technician class next Saturday.
All right, sounds good.
Same time, same place.
All right, thank you.
All right.
Thank you.
You too.